But I would talk about how to set up a system so that we can run distributed applications using WebAssembly instead of sort of the native architectural formats on a heterogeneous cluster. So let's talk a little bit why we would like to do this. So I'm interested in the cloud-to-edge compute continuum. So we have data centers, which are typically homogeneous, even though more often than not now you have multiple kinds of architecture also there. But then you have a host of devices and aggregation nodes and whatnot, where you have many different kinds of architecture and different kind of capabilities, different compute capabilities, resources, and so on. So we are interested in sort of making a more automatic service placement, because we don't think developers would like to specify exactly where their software is going, and we also would like these services to be reschedulable, or as needs come by, they can move. We are talking about multi-objective optimization. We want to specify things like cost, latency, and energy, and have that as criteria for placing services on compute nodes dynamically in runtime. And we also observe, as I said, increasing heterogeneity. In particular with CPUs, we have x86 and ARM. In Europe, they're quite heavily pushing RISC-V as an architecture. In many cases, there are several projects trying to build supercomputers using RISC-V with accelerators. And this is also big in Asia, in particular in China. Alibaba has a RISC-V processor that we are starting to work with also. And then we have a range of accelerators, and I have not really targeted that at all, but I have some questions at the end that I'd like to discuss with you who are more knowledgeable in the WebAssembly ecosystem. But all in all, this makes a case, we believe, for WebAssembly, schedulable WASM modules, and architecture-independent targets. However, the last Wasm Research Day, we looked more closely into the question, is the runtime performance of WebAssembly enough, or is it predictable enough for across different architectures? Many studies have been done on WebAssembly performance, but rarely where they compare how they on different hardware architectures. So we did that on x86, three 64-bit architectures: x86, RISC-V 64, and ARM 64. And overall, this was presented at Wasm Research Day in Munich in October, I think it was. And overall, we see that the different columns here are relative performance to native execution. So closer to the red line, which is 1, the closer to native execution we are. And majority of these 50-plus benchmarks show very close relation, except for mainly the green one, which is the RISC-V, which is not so mature. We concluded there that this was for Wasm time, so the crane lift compiler was probably not as good for RISC-V as for the other architectures. And then, there were a few benchmarks which were not good for anything. But overall, it's pretty good. We used these architectures. This is two, in particular, the NVIDIA card is pretty old now. I cannot get a Linux, Ubuntu later than 1804 to run on it. So that is a pretty old one. And this is a small RISC-V device. So I set out to use this setting also to create sort of a Kubernetes cluster, because Kubernetes is so far sort of the state of the art in terms of orchestrating containers, and I see Wasm modules as containers here. So if we look at what is involved in getting a distributed WebAssembly application up and running, so you have these different components in Kubernetes, and I'm assuming that most of you are familiar with most of this. And the only thing that is sort of architecture dependent here are the worker nodes, really. So the different worker nodes where you have different architectures, but still the components of Kubernetes here, the kubelet and the kproxy, are not really architecture dependent, but the architecture dependence comes in when the kubelet is executing the WebAssembly module. So we are using containerd as sort of the container runtime in Kubernetes. Actually, we're using the K3s Kubernetes distribution because it was a little bit simpler to install, although I may regret it now. Anyway, by tagging services with a runtime class in Kubernetes, I can tell containerd sort of what architecture is going to run for. And it uses a containerd shim, and in this case, I'm using the containerd shim for spin from Fermion. I think there was one from Fermion here. Yeah. So I probably want to talk to you a bit later also. But we used that one because that was the easiest for us to get working with. We also have the runwasi shim implementing the architecture dependence for containers for Wasm time, Wasmir, Wasm edge, and I think something else. But it wasn't working for WebAssembly 2 or WASI 2, so the runwasi. So instead, Spin had the same functionality that I wanted to have, namely the HTTP request. So that worked. So this way, we can sort of mix having containers and WebAssembly modules in the same cluster. So some nodes run pods which are native, and some can run WebAssembly modules, and they can communicate with HTTP and other communication protocols. Okay, so it looked easy on the outside, and I was very confident starting this. Actually, didn't start working on this when I submitted the abstracts, and this is how hard can it be, right? The first thing I did was to set up Docker with containerd runtime on each of the nodes, and that worked fine until RISC-V64. Well, actually, the first thing I stumbled upon was that Wasm time, both Wasm time CLI and the Spin sort of usage of Wasm time needed to be patched because the ARM node and the RISC-V node I had didn't have large enough virtual memory address space, so the memory pooling blew up, and I didn't find a good way of passing the command line arguments needed to for containerd to run it without using the memory pooling. So it needed to be patched, and I got help with that. Then I found that while I could use containerd on its own to run WebAssembly modules on RISC-V64, I couldn't make Docker call containerd in a way, or K3s, so that it could run any WebAssembly modules on its node. So sadly, I haven't been able to run on RISC-V64 with full WebAssembly support yet. Okay, so then I tried to see if I could find some little bit more modern system, see if it went better. I'm using a cloud provider called Scaleway. It's a French cloud provider. I chose them because they are the only one I know of that has RISC-V nodes. I use a small x86 node, a small ARM node, and then a bare metal RISC-V node. That's the only way to get it. And they are pretty much equal in terms of resources and memory. Actually, the RISC-V node is bigger than the other ones, if anything. And let's see, I can do a short demo here to see if to show you how it works. So here we have this x86 node which runs the master Kubernetes. So we have 2 nodes in it, and they should both be capable of running WebAssembly modules through Containerd. I cleared the cache of K3s so that there are no images downloaded. And the reason I do that is that you should appreciate live the difference between downloading a Docker container compared to a WebAssembly module. And I will start a Rust. So the demo application is very, very simple. It's an HTTP app that just replies with some stupid thing. That's all. It's still demonstrative, I think. So I'm running this app here, and we can see what we have here. We have service started, and we have 2 pods. So this is a replication of 2 on both. So it starts one on the ARM node and one on the x86 node, and this is a Rust Docker container which has been built to be multi-architecture. So it contains an image for x86 and an image for ARM. I again was not able to build it properly for RISC-V to contain 3 architectures. It was pretty much quickly started on x86, but it still takes some time on the ARM, if you can see here. And now, some 50 seconds later, it started to run on the ARM. And we can just curl it. And I think it runs on 80 here. No, no, this one on. Yeah, high, it says. So it's responding with something. Okay. Let's remove this and then go for WebAssembly. Okay, it's not Rust app, it's called, okay, pods, but we should have a deployment also. Okay, so now I'm in a different window where I have, can run a WebAssembly app. So this app is similarly just an HTTP server that it's basically the most basic spin up that replies with something. And I run it with 2 replicas, and it should be able to run on both nodes. So let's do that. And let's see what we have. Get service pods. Oh, they're already running. 7 seconds later. Or even less, I don't know. And they're running on each node, and let's see if we can get a reply from it. And this one was port 80, I think. And it's a yo. Yeah, it says yo DockerCon. So this is from a demo done by Nigel Poulton at DockerCon last year. Okay, so I guess it more or less works. So the striking thing here was the time difference, but I mean, you all know this. And if you look here at the Docker hub. The first image is the multi-architecture native Docker image. 2 images, each over 800 megabyte in a compressed state. And then you have this one, which is the WebAssembly module or the spin application in a compressed state, which is 500 kilobytes. But if you look at them inside the computer, when they have been decompressed, you see that the multi-architecture is 4.5 gigabyte. It should possibly be able to reduce this a lot, because this based on an image which has a full Rust toolchain in it, and you don't need it because it's a statically built application, but still. And the spin application is 2.5 megabytes. But if you do it with WASI HTTP, it gets down to 400 kilobytes. And here you can see even in compressed, so the difference between compressed state and the decompressed is not that big in terms of the WASI HTTP image. This I haven't been able to run as a Docker application. I've been able to run it in Docker, but not in Kubernetes, I should say. Where should I put? Okay, yeah. Okay, yeah, the difference here is that in the spin application, the HTTP server sort of runs in the application, while in this case, it's the HTTP server is on the platform in the runtime system. Now, so I've established that performance is good enough, that it should be possible to run in Kubernetes, although there are many sort of moving things that don't work yet. We've done some experiments in scheduling these pods so that we don't need to specify exactly where to run them. So we want to be able to explore different trade-offs in terms of cost, performance, network latency, bandwidth, and so on, where we had different nodes. So we extended Kubernetes with a custom scheduler that, based on certain criteria, chooses the node to place a pod differently than regular Kubernetes. And then we also have a rescheduler where we periodically sort of reevaluate these criteria and take it down and then put it on a new node if that is better. So this slide here shows one of these schedulers we have experimented with. This one in particular uses communication pattern as a, it measures, it takes some time in the beginning of the application to check the traffic pattern, and then based on this traffic pattern, it finds better or worse, better ways of placing the pods. So after some training time, we have an abstract communication graph and use that in our custom scheduler to place the pod in a node accordingly. We assume here we have services that are sort of, they start and then they go away and then they start again, so that they quite often need to be placed again. And we have multiple services. And then we have the rescheduler, which periodically sort of reevaluates this, because normal Kubernetes does not reschedule pods. It places them until they find executes, until they crash or go away for some other reason. But Kubernetes itself doesn't really do this. So what we found here is, well, I will not go through all the things, but compared to the baseline, we measured, in this case, the cost with some abstract cost measures. And the green bar here is the total cost. We have subdivided the cost otherwise in computing, networking, and the cost to execute the rescheduler also, which is negligible. But we show that we can, if you look at the green bars here, we show that we can reduce with this kind of method, we can reduce the cost significantly. And importantly, it doesn't come, these cost savings doesn't come with sort of any performance overheads. The thing is that we choose nodes which are good enough for the service level objectives of the application, which is sort of the goal here. Don't use faster or more expensive nodes than necessary. This is basically my last slide, and what I want to sort of bring to the table here, and would love to have discussion over these 3 days. Is this a case for infrastructure-less computing? It's a mouthful to say. Serverless sounds better, but I want to abstract away the whole infrastructure thing, if possible. Developers really don't want to know about servers, Kubernetes, or whatnot. They only care about how their software performs, and that they perform with the correct function and performance according to the service level objectives. And you want to save money or you want to save energy in the meantime. At the same time, I think infrastructure providers, they'd like to free themselves from the applications. They would like to be able to change the hardware. And I talked with the gentleman from, Toyota, during lunch. And you basically said the same thing, that you would like to change the hardware without affecting the software. So, and I think this could be a case, if the software is written in WebAssembly, that this could be a case for that. So we want to describe services in terms of constraints, for instance, like service level objectives, and capabilities, which are the software's ability to utilize the hardware features. And that information is very important for schedulers and reschedulers to be able to match the software with the hardware. And this is, for instance, ability to use parallelism, SIMD, accelerators, and so on. There are some challenges we need to solve. Most importantly for myself right now is to make sure that we have robust multi-architecture support. It's been very frustrating working with RISC-V in this respect, but it's interesting. If someone has better experience, let me know. I'm interested in exploring new ways of using accelerators and WebAssembly. You have WASI-NN, which is one way of doing it, where you build an abstract sort of interface, abstracting away everything which has to do with AI model inference. So that's one way. But could it be possible maybe to share memory somehow, open up a memory which can be used both by accelerators and WebAssembly runtimes? Is there a way to work with memory handles so that you allocate a handle which you can pass around in WebAssembly, but actually doing the heavy lifting, the heavy work in the accelerator, much like what Python and pandas are doing, where you have a handle to a panda data frame, never worked with in Python really, but only in the accelerator. And also the decision on what runs in WebAssembly and what runs in the engine. Wasm Cloud, for instance, are using a lot of things that, like the capability providers, where you put a lot of things running natively and then expose an interface to be used in the WebAssembly modules. So if you have any input to this, please talk to me, and I'm happy to discuss further. Thank you.
So I have some questions. So you presented last time about the hardware differences in RISC-V and ARM64 and running WebAssembly code. Did you think about scaling that that out to more devices in this class, or whether you could use the server infrastructure here, the cloud providers that you've looked at?
That would be interesting to do. I didn't have time to look into those things. We have enough troubles with getting RISC-V on board. But that's certainly something I would like to do.
Have you had any contact with the Wasm Time team? There are a couple of representatives here. They might want to look into RISC-V.
Not Wasm. Well, yes, but I forgot who I talked to.
We talked a bit in issues and around spin on RISC-V and
yes.
that working at all. And in general, yes, spin, but also definitely part of the Wasm Time team. And we should get you sorted on making all of this work on RISC-V. And that should all work. We should also redo the benchmarks ideally, because RISC-V should, I think, be a bunch faster compared to the better part of a year ago.
Alex has done a bunch of work.
Chris?
Really quickly, did you talk to the University of Messina at all?
No.
So there's a head of cloud computing, IEEE chair, Massimo. He's based in Messina. We used to do a lot of work with him. I used to do a lot of work with him in my previous life on cloud software infrastructure and workload placement. And I think a lot of what you're asking for the infrastructureless computing would overlap with some of the previous work that was done there. And this does look like a logical extension. So I'll see if I can dig him out on my LinkedIn and give you an introduction.
Sure. It would be good. There are some people in Crete at the fourth lab that work on Kubernetes, on RISC-V also, and they have been trying to get their pull requests approved, but not yet. Okay.
I have another question. So given that you had done some work on the scheduling costs, and I guess I assume that includes some migration as well.
Yes.
Does the lower overhead of WebAssembly change the equation there? Does it fundamentally make more things possible?
That's something we haven't looked into yet, because so far the scheduling work has been done only on native containers. Most likely, I mean, rescheduling now takes a pretty long time, because we have to take the decision to do a rescheduling of the pod, and then we spin up the new pod in a new location, and then we do a sort of rolling update in Kubernetes to shift the traffic from one to another. That should probably go faster with WebAssembly than with regular containers.